Okay, so right now it's 12 o'clock, and then that's us get start. So hello everyone. So welcome to the Eye and Perception session. We will be hearing 4 exciting papers about vision, perception, and XR. And we for each paper, they have 15 minutes, 12 minutes for presentation, and 3 minutes for Q&A. I will ring a bell 1 minute before the end of the 12 minutes to remind them, and ring twice, I think, to wrap up the presentation. And that's without any kind of delay. That's just start the first one. The first one is when one eye sees less, uncovering perceptual thresholds of asymmetric quality degradation in 4K XR displays. And we are we are happy to have the first author to present. Hei-Chang Lee, please take it over.
Hi, I'm really happy to have a presentation about our research today with the title of When One Eye Sees Less, Uncovering the Perceptual Threshold of Asymmetric Quality Degradation in 4K XR Displays. I'm Hei-Chang Lee from Kyung University, advised by Eui-Jong Chu, and the co-authors are Namir Kim and Hwesung Liu. We are seeing incredible advances in VR hardware. Recent devices such as Apple's Vision Pro and Vario's XR4 now provide ultra-high resolution 4K displays, which simultaneously raises the demand for high-quality image. However, this requires a lot of resources like processing power and network bandwidth, which in turn causes some critical problems such as system overload, heat generation, increased power consumption, and latency. To solve these issues, many research have been conducted to save some system efficiency while maintaining the overall visual quality. And studies about this, foveated rendering was often used, but applying it can create some noticeable boundary region between the areas with different qualities. And since utilizing this foveated rendering is not our main goal, so we decided not to use it in our study. Furthermore, our study explores how visual characteristics such as spatial frequency, brightness, and temporal index influence the visual quality assessment. Also, we used a video quality metric to determine the visual perception threshold. In this study, we propose an approach based on a quality adjustment. This can be done in 2 ways, by reducing the resolution or by increasing the compression rate. However, simply lowering the quality on both eyes negatively affects the user's experience and immersion. So we apply an binocular asymmetric quality adjustment based on the binocular suppression mechanism of a human visual system. When we see an image with different quality on each eye, our brain naturally focuses on the image with higher quality. So by using this, we just lower the quality on one eye to save some resources while maintaining the overall perceived visual quality. In this study, we adjusted the resolution by using the bilinear interpolation and adjusted compression by using a VP9 codec. For our experiment, we used 4 types of content, and we tried to choose some typical environment when we use a VR device. The first one is called a video clip, which features a bird's eye view capturing the movement of the vehicles. The second one is a gameplay video with a well-known VR game, Beat Saber. And the third one is an image. We designed it and converted it into a video which contains some typical elements used in VR interface. The fourth one is a web, and we also designed it and converted it into a video with a web page viewing condition in VR environment. For making the participants watch the videos with 2 different qualities in each eye, we positioned each video at the same location in VR environment and applied the separate layers to each one. And below is an example video of the trial, and the participants first watch the original video on both eyes, and then they watch a 960 pixel resolution video on the left eye while still watching the original one on the left eye. And this is an example of binocular symmetry quality degradation. The experiment was conducted with 41 participants within subject design, and we conducted each resolution and compression to each eye once, including resulting a total of 4 blocks. And in each block, participants compared all possible degradation levels once, and in each trial, there was 2 separate video presentations, and after participants watching the videos twice, they performed the 2 alternative first choice that they answered which of the 2 videos have a better visual quality by rotating a knob, left for the first and right for the second. We then analyzed these responses by using just objectionable difference, which is called JOD. And JOD generalizes the responses of a subjective quality assessment with the baseline of JOD 0 with the original video. So if the original video was chosen 75%, that it seems to have a better quality than the other video, the other one's JOD becomes -1. So it says that a certain video with a certain quality has a JOD value below -1, it means that the quality difference was perceptible compared to the original one. And here's the results. This graph shows the JOD results across all contents. And as I just mentioned, the -1 JOD on the red line in the graph means that if a certain distortion level below has a JOD value below this JOD1 line, it means that the quality difference was perceptible. And let's see the resolution first, the green line on the graph. At distortion level 3, the JOD value is approximately -0.6, but at distortion level 4 and 5, it becomes below -1, resulting -1.2 and -1.5, which means that participants can notice the difference if the resolution becomes under the 768 resolution. And in compression condition, none of the JOD values became below -1, which means that even when we apply the maximum VP9 compression in one eye, participants could not notice the quality difference compared to the original one. In more detail, we analyzed the JOD results for every content, and the game showed the opposite results compared to the others, that in resolution, none of the JOD value became below -1, and the other 3 had that, starting from the level 3 and level 4. And conversely, in compression condition, it was the only game condition that has a JOD below -1, starting at level 4. And to make our results objective, we chose to define it using a video quality metric called the VMAF. But we do not know the exact value where JOD becomes -1, so we tried to determine it by calculating it using a psychometric function, resulting in a VMAF score of 46.76. Then we performed an additional test to validate our results on new content. We selected 7 new videos, and we created 2 different versions. Level 1 for the quality above our threshold, and level 2 for the quality below our threshold. And furthermore, as you can see in the figure on the right, the videos have diverse characteristics. The validation results were clear. For level 1, which has a better quality than our threshold, resulted in a JOD value above -1, which means that the quality difference was not perceptible. And level 2, which had lower quality than our threshold, had a resulting value of JOD below -1. So the discussion, without considering the content type first, only resolution level 4 and 5 showed the quality difference was perceptible. We think that this is because of a binocular suppression mechanism, that for moderate degradation, such as compression and the resolution condition from 1 to 3, the original high quality image in one eye successfully suppressed the low quality image in the other eye, making the users could not perceive the difference. But for critical degradation, such as resolution level 4 and 5 in this study, the visual conflict is too large that it overcomes the suppression effect, making the quality difference was perceptible. And why did the game show the opposite results compared to the others? We link this to its video characteristics that game had a low spatial frequency, low brightness, and a high temporal index. For resolution, we think that this high motion and low complexity likely to erase the blocking artifacts caused by the resolution degradation and making it imperceptible. And conversely, in compression, we think that this high motion and low complexity making the loss of detail more obvious. In conclusion, we found that users do not perceive the quality degradation in one eye up to a certain threshold, which is a resolution of QHD and compression of CRF63. Our research confirms the potential of binocular asymmetric quality degradation in VR. Thank you for listening. If you have any questions, feel free to ask. Thank you.
So any audience have question for our author? Can the student volunteer to hand over the microphone to the, okay.
Thank you for the presentation. I was curious, you showed that you collected data on dominant eye in the beginning. Did you consider separating out values for those who had right and left dominant eyes to see if that impacted the results at all?
Yes, of course. We actually analyzed the effect of the eye dominance in our paper, but we did not include it in our presentation today. And the results said that there was only an effect of eye dominance was significant in resolution distortion level from 1 to 3. That we think that the visual acuity difference in both eyes only affect the visual quality even in only a moderate degradation. And if the degradation is critical, we could not find any significant effect of eye dominance.
Awesome, thank you.
Thank you.
Thank you for excellent work. And I found your results very interesting in the domain of gaze contingent of aviated rendering. I'm not sure if you're familiar with those techniques, but am I correct in interpreting your results that if such methods that conserve battery power by tracking the eye, and let's say if there is mismatch in one eye, let's say it's not dominant eye, then those degradation errors might be actually not bad. Like they would not be perceived very badly because, let's say, if you track the dominant eye accurately, then the person would not be able to perceive the difference. And why it's significant? Because by degrading sort of more non-dominant eye, potentially you can save even more computational power and then extending your battery life longer. So am I correct in interpreting the significance of your results potentially in this way?
Yeah, I think you have the right point, and we try to analyze this specifically, but we think we only use the 4 types of contents with limited video characteristics and limited time of video presentation. So we are going to study about the effect of eye dominance with different kinds of contents later. Thank you for the suggestion.
Thank you.
We probably can take one more short question. Anyone? Okay, so if not, I have one question. So Zhenshuo Liu here. So in your paper, you mentioned, if I remember correctly, it is mentioned that H264 is selected. So is there a specific reason you use that compression method?
Sorry, we should say that again, please.
Yeah. So for the compression standard, is there a specific way you select H264, or it is just because that is commonly used?
Codec of H?
Yes,
oh.
the codec.
Yeah, we chose the VP9 codec because we thought that it was the quite modern and great compressing method to use in our experiment. And yeah, That's why.
Gotcha. Yeah, thank you so much.
Thank you.
Yeah. So let's thank the author again, and
There we go.
okay,
All
please
right.
take it over.
Hello, everyone. My name is Matthew. I'm from Colorado State University, and I am presenting our paper on examining eye vergence and using eye tracking during perceived depth changes with optical see-through augmented reality. To start us off, a little bit of background. In depth perception and augmented reality, there are several issues that persist, and these cause misjudgments when it comes to perceiving depth relative when in the AR object relative to the real-world counterpart. Now, we don't have it pinned down exactly what all of the causes are for these misperceptions. Several reasons could be vergence accommodation conflict, lack of depth and environmental cues, as well as method of measurement, and several others. Now, as a base knowledge for depth perception, accommodation and vergence are the two primary near-field depth cues that are used by humans. First off, accommodation is our lens flexing and relaxing to focus at the correct depth and make sure the information is not blurred and is nice and sharp. Now for vergence, that's the rotation of our eyes, left and right eyes, in and out, diverging, converging, to make sure we don't get any double vision. We have a nice, clear view of the information. Now, some previous work looked into the comparison between a objective measurement technique called eye vergence angle. This uses vergence to, when information is displayed at a certain depth, we can track the eyes and gather vergence. And on the right side, we can see several participants' data from this experiment. Now, as you can see, there's a wide range of results that were seen across all participants. They had values ranging from around 30 degrees down to 5, which is unrealistic, and people don't have that different of values. They also found a lack of generalizability across OSTR devices and eye trackers, as they only use one eye tracker and one device. We did a partial replication on this prior study using the same exact tasks they use, the same depths, and the same vergence calculation methods. However, we also expanded on this work by including two different headsets, commercial headsets, the HoloLens 2 and the Magic Leap 2. We also used the built-in eye trackers instead of a separate eye tracker to compare between these, as well as a systematic approach where we only displayed one virtual object and one depth at one time when they were giving verbal estimates, whereas the prior experiment showed all distances at the same time when asking for those verbal estimates. Now, for our research questions, we looked to see whether our objective measurement of vergence and our subjective measurement of verbal estimates were consistent with the depth of real and AR objects for our first question. And our second looked into whether objective measurements were generalizable across either the devices or the individuals. Now, for our experimental task, we used an alternative forced choice task. We had first displayed the letter C, and this would be rotated in one of the cardinal directions, so that the opening of the C would be either right, left, up, or down, and the participant would be instructed to input on a keyboard the direction of the opening of the C. Once they completed that, the C would change into an X, and they were instructed to look directly at the center point of the X, and that would last for around 3 to 6 seconds, randomized, and then that would disappear, and it would move back to the letter C and change depths, and they would continue this until all of the tasks were completed. For the variables in setup, we used different environments, which consisted of a real environment and an AR environment. You can see in the image on the bottom right, the left is an example of the real-world environment where information was displayed on monitors in front of the participant. On the right two images, you can see two images taken from within the devices of the HoloLens 2 and the Magic Leap, which were our device conditions. The third condition was distance, which we used 0.35, 0.75, 1.5, and 4 meters. And we displayed these using what we call depth pairs, which you can see on the right side is just taking those depths and putting them into converging and diverging pairs. And these pairs were each displayed an equal number of times for every single participant. For our dependent variables, we used the eye movement data to track vergence. This consisted of the gaze direction from each eye, the eye location of each eye, and timestamps, as well as some other information. We also tracked the accuracy to make sure the participant was actually engaging the experiment and paid attention and gave the right inputs. And lastly, we collected verbal report data. For the design and participants, we used a within-subject experimental design, and we used a Latin square to counterbalance our device and environment. Now, Latin square is essentially just making sure there's no learning effect between each of the conditions. And each depth pair was shown in a random order, but an equal number of times. For the participants, we had 20 participants, 15 men, 5 women, and the ages ranged from 20 to 19 from our local college. And for measuring the divergence, we used the 2 gaze direction vectors. These were unit vectors, and as you can see on the right side, the divergence angle is that angle that the vectors make meeting at the location of the object which the participant is looking at. And using the equation displayed on the left, we calculated what the divergence angle was. Now for our results, between the divergence angle and the verbal report, we used a log ratio to normalize this data and compare between the AR and the real data. And this allowed us to actually directly show comparisons in underestimation and overestimation between EVA and verbal data. We also separated out the HoloLens and Magic Leap data to compare between the devices. And from this data, we found no significant difference between either the EVA or verbal estimate measurements. We just found consistent across all data. This interestingly contradicts the prior work, where they found the EVA data was more consistent and more accurate than what was found with the verbal data. Now for per device variability, we found a significant amount of variability. There was, as you can see on the left graph, this shows EVA against the end depth, and the HoloLens had a significantly higher consistent EVA across all participants, whereas the Magic Leap kept a lower EVA values. The black line there displays what would be expected from an average IPD from eye tracking, as just a baseline, and the focal plane is displayed there as well. We did find a nonlinear relationship between the depth and EVA, which is consistent with how we would expect to see from our eyes. And reasoning for this, in the bottom right corner, you can see several differences between the device's eye trackers as well as their displays. These could be several of the reasons for why we're finding these results. Now for per participant variability, we also found a lot of variation between this. On the right-hand side, you can see just an example of 7 participants data. And the Magic Leap has some variability, especially within participant 4, as you can see here. And within the HoloLens, we saw much more variation when it came to the closer distance, with some of the values dipping down when they should be dipping up as expected by correct divergence values. And this does match reports by the prior works where they also had significant variability between different participants. Now for our limitations, we didn't have too many participants and we had a very limited pool. So ideally, we would have had a much larger pool and more generalizable participant pool. We also ideally would have been able to use a perceptual action task instead of just limiting ourselves to verbal report, which has some less accurate values usually. And we also used the physical monitors, and they were still still in view when the AR information was being displayed, which could have confounded the EVA as well as the verbal reports. And lastly, we didn't exactly look for divergence accommodation conflict. So future work could specifically search for this, this impact. As for our conclusion, yes, we did find consistent values across our EVA as well as our verbal estimates. And for the generalizability of devices and individuals, we said no. There was way too much variability between both the devices as well as the individuals' data. And these are the authors. Thank you to everyone who helped with the paper. Dakota is also here, so if you find either of us at the conference, feel free to come ask any questions or talk to us about our work. And thank you.
Yeah. So let's move into the Q&A session. Any question?
Yeah, I wanted to do a small comment. As a person who worked on Meta Quest Pro at Meta, usually product team optimizes for a specific depth, and so that's why you see, some performance like better and some performance is worse. And so, but that is a great study, and the fact that you have variability, my only suggestion, try to capture things within the operational range, because it looks like you did everything like in the center.
Sorry, what was that?
When you measured versions, all the targets were presented at the center of the vision, right? You did not investigate the operational range.
Yeah, for the most part, we stuck to just,
Yeah.
the center of view.
And that is something would be very interesting and very novel to do. And if you do this, try to think about it as like percentile term. So think about it as like P95 percentile, because that is the most impactful number, let's say, for the product team.
Yeah, that would be really interesting future work. Thank you.
Thank you.
Do you want to go?
Yeah, this is really, really cool. How many different examples of the display did you use? Did you have like one HoloLens 2 and one Magic Leap 2, or did you try different HoloLens 2s and different Magic Leap 2s?
Different devices of like the same. We just used one of each device.
Right,
so-
okay.
yeah.
I'm not sure if this is true of the current generation of headsets, but I was co-author of a paper with Mark Livingston and Steve Ellis, VR 2006, where we had a whole bunch of these Sony headsets, and we discovered huge variations, relatively huge, between what's supposed to be the same model of headset, presumably because of the way in which they were assembled. So I'm wondering if the paper you were comparing with, did it use one of the same headsets you used?
The previous work used only the HoloLens 2.
Right. So I'm wondering if your HoloLens 2 and their HoloLens 2, right, might have
Yeah.
been different, and that might partially account for some of the difference. I don't know how much variation there is between them, except to know that I've had HoloLens 2s that have been sent back because of issues.
Yeah, absolutely. And they used a Pupil Labs tracker, whereas we did use the built-in eye tracker.
Right.
So the eye trackers aren't really as comparable, but yeah, the
Yeah.
display absolutely could be.
Okay, thank you.
different, which is interesting. Thank you.
Hi, it was a nice talk. Thank you for that. My question is related to the study design. So the paper that you're comparing it with, was the study in that paper done within subject?
Yes, I believe it was within subjects as well.
Okay,
Just
and you also did within subject. Now, you didn't get a significant effect of, for the first analysis that you showed. So can you like speculate that maybe there was some carryover effect across the condition that the participants received? That's why you might not have received significant result.
There absolutely could be. Let me pull it up. Yeah, there absolutely could be. We specifically, we tried to remove any like learning bias or anything like that by doing our Latin square. So hopefully there wasn't any impact from just like learning throughout the experiment. But there's absolutely a chance that that did come into play in our data.
Thank you.
Thank you.
Yeah, so because we're running out of time, so let's thank the author again.
Let's jump right in. Virtual reality in general allows us to immerse ourselves in three-dimensional virtual worlds. However, there's a challenge that arises from this three-dimensionality, which is that the content that the user is supposed to look at is not always in their focus, as it can simply be obstructed or out of view. To remedy the situation, there exist so-called gaze guidance techniques which try to shift the user's focus toward a specific location. Here in the image on the right, you can see a very well-known gaze guidance technique. It's simply an arrow. These techniques, however, have a challenge themselves, which is that they are either very efficient in what they do or they are more subtle. As you can see in the arrow, it's certainly efficient in telling you where you're supposed to look, but it's not very subtle in doing so. This is where our idea comes from. We propose to use spatial distortion to guide the gaze in virtual reality. By distorting the space, we do not actually have to obstruct any content itself, since we only distort space. We do also not have to manipulate or add any content in the virtual scene, like adding meshes. And our spatial distortion is dependent on the gaze, the current location where the viewer looks at. So we only distort space in the peripheral area to keep the immersion of the user high. Furthermore, our technique works entirely in screen space. But before I get further into our technique, let's talk a little bit about related work. Generally, there are three types of gaze guidance techniques: overt, subtle, and diegetic techniques. Overt techniques are the ones that you've already just seen in the introduction slide. Those are the really easy to see techniques and like a big arrow. These techniques generally work really well in what they do, but the downside is that they can, as I already mentioned, occlude content or simply have a very negative impact on immersion, since you would not expect a red arrow appearing in your virtual world suddenly, just like in the real world. To address this challenge, there exist subtle techniques. For example, here we can see in the image a subtle technique called dead eye. This technique renders the target object that's relevant only in one eye of the user, to kind of create a highlighting effect to shift the gaze towards that location. These techniques attempt mainly to have no negative impact on immersion, but the downside comes from the subtlety itself, their lower efficiency. There also exists a third type of techniques, so-called diegetic techniques. These techniques kind of try to combine overtness with subtlety by overlaying or by using diegetic meshes, for example, like a dog that tells the user where they're supposed to go. So the technique itself becomes part of the world. So the technique can be very overt, but still somewhat subtle in what it does, since it does not interrupt immersion. The downside of these techniques is that they cannot be generalized, since you would not expect a dog in a space simulation, for example. So with that, let us get to warp vision, our proposed technique. We distort the space around an object to guide the attention. So for example, if you look at the image on the left here, location you might very well know. If we want the user to, for example, look here towards the left side in the circle, in a very simplistic case, we would simply distort the space around this area. This spatial distortion is dependent on the gaze, as I've mentioned in the introduction. If you look at the right image, you can see this black eye symbol on the left, and the distorted target that the user is supposed to look in, this orange sphere. And as the gaze approaches the object, the distortion becomes lowered. This way we can ensure that the immersion actually remains unaffected. Our technique offers multiple parameters. They can be found in the paper. Just a quick overview here. Generally, we have a radius. The radius of the technique determines how much we actually want to distort in the peripheral area, and is also the parameter that depends on the user's current gaze position. There's also another parameter for the curvature, which is kind of the strength inside the radius, how strong we want to distort the area. Then there is an increase and decrease parameter, so we do not actually distort the area directly proportional to the gaze position. So we set the radius kind of with an increase and decrease, so it can smoothly change the distortion. And lastly, there's a growth parameter. This parameter determines how strong or steep actually the curve is of this distortion. Currently, we use an exponential distortion, so the further the user looks away from the target, the stronger the distortion becomes. You can also see a property of our technique in this last video on the bottom right. It actually also works for out-of-view targets, since we distort space outside of the view, and the target object itself does not need to be immediately in the view to create this distortion effect. The implementation of our technique is fairly simply done in Unity as a post-processing shader, which contains the entire logic, which distorts the space in screen space, and a script which contains the logic for the radius and how the radius changes depending on the current user's gaze. You can also find more information on that in our GitHub repository, where everything is open sourced. We did a perceptual study in 2 different virtual environments where we asked the user to find a certain target. So here, for example, in the left image, the user sat in front of 500 geometric objects, and we asked the user to locate a singular sphere which was placed exactly once among these 500 objects. In our other environment, we put the user in front of a table and asked the user to find a certain coin among other coins. Due to time constraints, I will focus on the first study in the artificial environment. Here, the user was supported in their search task in 3 different ways. One simply being we actually did not support the user at all, so we get a baseline and we know how long the search would take the user without any assistance. Then we used a comparison technique, which I already mentioned in related work, which is called dead eye, a subtle technique, just as a reminder, which renders the target object only in one eye. And finally, we evaluated 4 different settings of warp vision, which we chose based on a continuum ranging from a very low and subtle distortion of the space to a very high and overt distortion of the space. Here you can see our results as simple mean and median search times with the different techniques on the bottom. For example, without any assistance here in our first environment, you can see that on average a search took around 55 seconds for the user, and the white bar shows the median with around 25 seconds. If we supported the user using our comparison technique dead eye, you can see that the median drops by around 1/3 to around 25 seconds and the average as well. Compared to that, you can see a significant differences, here called warp vision min, low, medium, and high, are for warp vision settings which we used. And for all of our settings, the search time is significantly reduced. Even with our very minimal setting, which is only a very subtle distortion, you can see that the median search time drops below 10 seconds. And if we distort the space even further, you can see this goes down to 3 seconds. We took a closer look at how people actually search the target. So we employed survival analysis using the Kaplan-Meier estimator. In case this is not very well known, I will give a brief example. This analysis, these curves tell us after what amount of time a certain event did not occur yet. So for example, the blue curve here shows us the curve without any assisting technique. And you can see, for example, that after 1 minute, there's a probability of 35% for the user to still be searching the object. At the same time, if we look at the comparison technique dead eye and our very low intensity warp vision setting, you can see this probability that the user still be searching drops significantly. Even with dead eye, it's only around 20% after 1 minute, and with our technique, it's less than 10%. If we employ even higher distortion settings to guide the user's gaze, you can see this very stark downward curve here, which shows that even already after 10 seconds, the user has already found a target with a probability greater than 85%. Just quickly, I was talking about significances. Where are they coming from? We used the pairwise Cox proportional hazard regression between techniques to look at significances. And we could see that all of our warp vision settings improved the search time significantly compared to the unassisted search, which was not the case for dead eye. We also looked at subjective data. Here I want to quickly talk about the immersion disrupting property of warp vision. You can see a semantic differential scale here. We collected this data by asking the participants after each search task how interruptive they felt this technique was. And you can see that our lower intensity warp vision settings have almost no impact on immersion at all, with a median of 0 and 1. And even the high intensity warp vision settings are fairly similar to our comparison technique dead eye. There are more results on cyber sickness and pre-attentive visual processing you can find in the paper. So let's talk about limitations and outlook. One limitation is we have limited out of view guidance. I mentioned our technique can guide outside of the view. However, we currently in our implementation only do this in the forward-facing hemisphere simply due to 2 reasons. One being that if the target would be directly behind the user, the question would be where would you actually try to distort the image to effectively guide the user behind them. And the other issue is if the object is also outside of the view and you would apply a very stark distortion, it could happen that null space or black pixels could get distorted into the screen space, which is something that we obviously do not want. Nevertheless, we could, for example, use intermediate waypoints to guide the user very far outside of their current field of view. Another limitation comes from stereoscopic disparity. Applying a distortion in a stereoscopic head-mounted display can is unequal. since it's fairly difficult to actually apply equal distortion. Nevertheless, since our distortion is only applied very peripherally and never in the direct gaze of the user, we actually did not have a single participant who noticed any disparity in the distortion whatsoever. Also, another point is the depth perception. The question remains, does it actually impact the depth perception whatsoever? As I mentioned in our study, we could not actually see any impact on that. Another issue are challenging surfaces. For example, it can happen that if you want to guide the user towards a surface which is just simply a black table or something, it would be very difficult to distort space if there is nothing really to distort. Same for dim lighting. And the question remains, maybe we could use other types of spatial distortion for guidance.
Yeah, sorry. So, well, because I think we are running out of time, so we will need to move to the Q&A session. So, do anyone have a question for the authors? Please go ahead.
Quick question. So your technique works for the static image, right? It doesn't work for the video. And if that is the case, then how to apply it to a video or dynamic image? Sorry? Oh, okay. So the way I understood it is your technique works for the static type of environment, but what for the dynamic environment, like a game or video?
Yes, our current study is in a static environment. We have actually done a recent study again to reevaluate the technique in a dynamic scenario where the user could freely turn around and we had objects that moved and also target objects that moved. And our technique was actually working, I would say, even better in these scenarios, since the distorted space kind of changes and you have these contrasts in background. So it's actually very efficient, even more efficient in dynamic scenarios, yes.
Hi. First of all, thank you for that very interesting talk. I have two, actually. One is very easy to answer. I didn't get the number, how many participants you had in the user study?
20.
20, okay, thank you. And the other one is like more for Outlook maybe. I would be interested in if you ever have tested that approach for augmented reality, because I could imagine if you have a video see-through HMD, right, it's also particularly easy to manipulate the screen.
Yes, it's actually one of our to-do list. On our to-do list, we want to try it in a video see-through through like a Quest 3, for example, and check how that works exactly. That's also was one of the big motivations why we actually only curved the screen space, so we could actually apply it for exactly these use cases.
Yeah, okay. But you need eye tracking, right?
Yes, you need eye tracking.
Yeah, okay, Quest 3 doesn't have eye tracking, but...
Exactly, but well, you can kind of, there are...
Yeah, solutions. We also bought something for having eye tracking in Quest 3. Yeah, okay. But nevertheless, thank you for the talk.
Yeah, we have time for one very short question. Please make it short.
Yeah, sure. Thank you for the talk. Oh. You can go ahead. You can go ahead.
Sorry, I really enjoyed your presentation. Thank you. I was just wondering, you just used some 3D shaped objects in your experiment. Would it make any differences if you just use some text-based 2D UIs?
You mean instead of 3D environment, just a two-dimensional environment?
No, in the 3D space, you just pop up some text floating around the space.
That should work in the same way, actually. I don't see a reason why that should not work. Since we curve only 2D space in the first place, so we do not actually require an object to be three-dimensional, if that was your question.
Okay, thank you.
Okay, so thank the author again for the very inspiring work, and in fact we do have lots of questions coming up. Please continue that on Discord or after the session.
Okay, good afternoon everyone. My name is Bruno and I will present the work How Accurate is the HoloLens 2 as already spoken. I am from Brazil, from Federal University of Alagoas, and this project was conducted in a partnership with Edge. So, mixed reality is being widely used nowadays and mainly in medical, industrial, and in education domains. And in these scenarios, important tasks are hologram placement and superposition to real-world objects. And those tasks, they are directly dependent on good depth estimation and self-localization. And errors in these tasks can compromise safety, can cause product defects, or invalidate industrial and medical procedures. So recent approvals have been issued, for instance, by the Food and Drug Administration from USA, allowing AR to be used in surgical navigation and surgical procedures in general. So this is another example of the importance of the field. But there is some gap, mainly in two areas. In data, because different works working on the accuracy of the device, they present different results, which vary from sub-millimeter to centimeters, and also in approach, because they mainly use different approaches such as fiducial markers or external cameras, or even handheld movement to compute the accuracy. So they are hard to reproduce. So this comes our motivation, which is to provide a robust, standardized, and repeatable measurement approach for analyzing upper bound accuracy of mixed reality devices. So our proposal is based on industrial robotic ground truth, where we couple the device to an industrial manipulator, and we aim to analyze the errors subjected to sensor occlusion, obstacle distance, speed, and axis of movement. The two main errors that you are interested are depth estimation and internal localization errors. So in our case, the MR device was treated as a black box, in which we have the inputs and the outputs, and we want to analyze the subject effects of the inputs over the outputs. So for that purpose, we defined some trajectories to be performed by the robot, and we measured the errors on those trajectories. We mainly defined the circular trajectories in two-dimensional and sinusoidal trajectories in one dimension. And for other trajectories, we consider three different speeds, based on a work by Batayashi. So this is more or less the setup of the robot. We couple the device physically to the effector of the robot using 3D printed mechanical interfaces. And the trajectories, they are devised in Cartesian space, and using ROS Moveit, we translate those trajectories to robot-specific joint space trajectories. These are the trajectory descriptions that we just mentioned. And in order to simulate failure over sensors, we chose to test failures over two specific sensors, which were the RGB camera located at the center of the device, and also the depth time of flight camera located right below the sensor. So the way that we simulated the failure over those sensors was basically to put some tape over the camera to occlude the vision. And for instance, we have 4 different combinations of sensor occlusions. The first one, SIRD, stands for no occlusions at all. Then, for instance, SIR stands for only RGB and spatial input sensors are good and depth is occluded. And SI is both RGB and depth cameras occluded. As we discussed, we are interested mainly in 2 variables, which are the distance estimation error and the internal localization error. For the distance estimation, we use the raw data from the depth cameras. We put an obstacle in front of the camera, and by looking at the depth histogram, we find the most frequent value, which we assume to be from the obstacle, And then we find the interval of lower and upper boundary from that depth value, and then we average the depth. This is more or less the setup that we used. We put the vertical obstacle in front of the device in 5 different distances, varying from 30 centimeters to 1.5 meters. And this is more or less the result of the process that we use to estimate the depth, the estimated depth for each time sample. So we have the RGB vision, we have the depth vision on the bottom, and then we perform the segmentation using the histogram, the most frequent depth over the depth image. Now, for the internal localization estimation, we compute the tracking position with the ground truth trajectory of we compared the tracking position with the ground truth trajectory of the robot arm. So orientation from all the trajectories are kept constant, and we analyze a best case scenario. So we remove any offsets between the ground truth and the estimated position, and we also eliminate drift cases. So in this case, we are comparing only the intrinsic hardware capabilities for tracking position. This is an example of 2 different sensor configuration data acquired for the trajectory H, which is a circular trajectory varying the Y and Z axis. For the SIRD and for the SI sensor combination, and here is the error between those estimated tracking positions and the ground truth position given by the robot. So for the distance estimation problem, this is the summary that we got. Basically, we have different values between the static scenario where the robot is stopped and the dynamic scenario with the trajectories. So we have 95% of the data for the dynamic case of the error is below 15 millimeters. The best obstacle distance were around 1.5 meters for the static case, and it was 600 millimeters for the dynamic case. We also found that occluding RGB camera in the depth estimation, it gave a slight increase of error. And for the velocity range, we noticed no difference between moving slower or moving fast for the depth images. And lastly, the circular movements, especially along the z-axis, tend to present a slight decrease in the errors and variability. So these are the overall errors captured for the static on the left column and dynamic trajectories on the right column. And these are the data grouped by the different input values that we discussed about. Something to mention is that for the internal localization assessment analysis, there were more samples than for the depth estimation. And that was because the depth analysis took into consideration the capture frequency of the camera, which was lower than the spatial input. So in this case, we collected around 3,000 samples. And the average error, 95% of them were below 13 millimeters. For the obstacle distance, the lowest error in the localization tracking was for when the obstacle was closer to the robot, closer to the camera. For the sensor configuration, we noticed that the highest accuracy was for when the depth camera was occluded for the SIR configuration. And for the optimal working distance, the 1.5 meters distance performed best in both static and dynamic tests. But for the static, the 600 millimeters was slightly better. For the movement axis, movements along the x-axis displayed higher errors. And for the velocity, we noticed a linear characteristic of the arrow, which increased with velocity. So these are the overall error computation. And these are the error computation grouped by variables. So the key insights here is that for the depth estimation, the error 95% was below 15 millimeters, and for internal localization, it was below 13 millimeters. And 2D movements are better for depth estimation, while 1D movements are better for tracking, and slow and smooth movements improve tracking accuracy in general. And sometimes more sensors might not always be better. So to summarize, we proposed a cross-device benchmark replication methodology that takes into consideration distance estimation error and internal localization error. And we validate it with the HoloLens 2 device. As limitation, our work emphasizes the best case scenario error, not taking into consideration drifts nor initial orientation errors. The orientation is kept fixed, and a single device was used. For future work, we intend to extend for multiple devices to investigate the long-term drift robustness and to consider replicating more natural human head movements. Thank you.
Yeah. So thank the author for the presentation. Do you have any question from the audience?
Hi, thank you for the nice talk. So I'm trying to understand the application aspect of the results. So do you expect the results to be like automated onto the robot, or to increase the precision of the robot, something like that? Or do you want this result to be taken to users, and users, when using the robot, will take care of the precision, something like that? So what's your thoughts on that?
Okay, thank you for your question. The main goal of this is to propose a methodology where we can analyze and validate different devices, different XR devices, because there is still a lack of solid methodology so that you can validate how accurate is the device. And then there is also a lack of knowing which tasks can be performed because you don't know how accurate the devices are.
Okay.
And so we proposed something that is repeatable and can be used for multiple devices, for instance, different glasses, and so that you can easily compare them using a robot, so that the movements are repeatable and the accuracy of the industrial robot is very high as well. So the main goal is that you can characterize better XR devices in general and understand how capable they are of performing tasks in the industry and in medicine in general.
Okay. Just a follow-up question, if nobody has a question. What do you feel this methodology will impact the production cost of the robots? Because most of the robots take like a lot of money to get developed.
Mm-hmm.
So how do you think it will impact the production? Yeah.
Sure. Yeah, in my opinion, it will not impact directly the production of robots, because they have a role in society which are for industrial environments or for being used in automotive fields and other tasks in general. So our proposal is to leverage something that universities already have. For instance, university that has the robotics course, for example, they have this robot manipulator. So it's to leverage something that is already there so that we can test other devices, other XR devices.
Okay.
But yeah, I don't think that it will impact a lot the production cost of robots.
Thank you.
Thank you.
Okay, so yeah, since right now it's already 1 o'clock, and so yeah, that was thank the author again